Good morning, everyone. My name is Ilerioluwa Giwa, and I am a PhD student at the Louisiana State University. Today, I'll be making a presentation on the performance characterization of self-reinforced printing material for construction 3D printing. This work was done in collaboration with my advisor, Dr. Ali Kezemian, and in collaboration with other professors at the Concrete Research Lab at LSU. Okay, so a quick overview of my presentation. I'll be discussing mainly about the reinforcement integration techniques compatible with construction 3D printing before describing our self-reinforced printing material, and then I'll be presenting and discussing some of our results on the performance characterization of this self-reinforced printing material. Of course, construction 3D printing has the potential, to transform the way construction is being carried out. This is because this construction technology offers so many advantages, which has incentivized the use of this construction technology in building construction, also infrastructure construction as well. Concrete is a very popular material for construction 3D printing, and we are very aware of the tensile limitation of concrete. So this necessitates the integration of reinforcement or rebar into the concrete mixes. However, one major challenge with construction 3D printing, which hinders the wild adoption, is the integration of reinforcement into the construction 3D printed structure or element. This is because manual integration of reinforcement is incompatible with this automated process, and also there are proposed integration techniques which are still, very early in terms of research and development. At present, so many researchers have developed so many integration techniques, and these techniques can be broadly categorized into three different categories. That's integrating reinforcement before the construction 3D printing, integrating reinforcement during the construction 3D printing, and integrating reinforcement after the construction 3D printing. So this slide right here shows the three, an overview of the three classifications. To my father's left, you can see integrating reinforcement before construction 3D printing. That's you basically pre-installing your rebars and then printing around the rebar. Or you can also integrate in parallel or simultaneously with the construction deposition process. And finally, you can also integrate your reinforcement after the construction 3D printing have been carried out using different techniques like post-tensioning and other exoskeleton framing systems. Of course, there is no one-size-fits-all in terms of reinforcement integration. Different application would require different reinforcement integration technique. And as a form of evaluation, you can evaluate all these proposed integration techniques based on the degree, the level of automation it offers, the architectural freedom of geometry compatible with the system, the implementation cost, structural loading under different loading condition, and of course, the process speed, because this is an automated process. We do not want to interrupt the printing process just to integrate your reinforcement, and definitely the continuity of reinforcement is another important criteria. So, of course, there are lots of integration procedure. One way of integrating reinforcement is, and a very simple way of integrating reinforcement is by using fibers, using discontinuous fibers as a form of self-reinforcement to the concrete matrix. So this provides a form of self-reinforcement, and it basically is a very simple way of integrating reinforcement during the mixing procedure of when you're preparing your concrete. Of course, there are various types of fibers commercially available, and also these fibers have different classification depending on your application. So fiber reinforced concrete offers a lot of advantages. It can help us eliminate any manual effort with the automated process. It can also be used to, reduce or supplement the use of rebars in structural applications, and in some cases, it has been used to, completely replace rebars. And also, depending on the type of fiber you're using, if you're using steel fiber, you can gain a lot of significant, increase in mechanical properties, and also some other types of fibers like synthetic fibers can be used to control shrink rate cracking and drying cracking. And overall, using fiber reinforced concrete can improve the durability and also the long-term performance of your structure. So for the focus of our research is using steel fibers as a form of self-reinforced printing material. Of course, using steel fibers with construction 3D printing is not new. So many researchers have also worked on in this domain, and like this study right here shows that you can actually improve your mechanical performance with using steel fibers at high dosages. Another study has also investigated the effect of printing parameters while using steel fibers as a form of reinforcement. And with this study shows that you can actually improve your fiber alignment during the construction, the 3D printing, which is, improves your mechanical performance as well. And also, anisotropy is well reported, especially when you use fiber reinforced concrete. So many studies have reported anisotropy, which is basically different readings from different loading direction as a result of fiber orientation, and it has also been closely associated with due to interlayer porosity from the printing procedure as well. So the main objective of our research is actually to investigate the fresh properties of steel fiber reinforced concrete as a printing material at different fiber dosages, and also to look at the mechanical properties of this steel fiber reinforced concrete as a form of self-reinforced printing material. The image to the right is the 3D printer we have developed in our lab at LSU. This printing system was basically developed by my very talented advisor, basically developing this printer from scratch. And of course, this system uses a screw type extrusion system with a user interface, to basically control your printing parameters. And another major feature of the system is we can actually customize the nozzle size, to fit whatever printing need we have. So a little bit about our steel fiber reinforced material as a printing material. This material comprises of type 1 and 2 Portland cement. We have a nominal sand size of 1 mm. We've used limestone, water, and then we selected the straight steel fiber with a length of 13 mm and a diameter of 0.2 for this. And also, we also employ the use of PCE-based superplasticizer, to control the flowability and workability. And then after so many preliminary experiments, we came up with this experimental design. We investigated the steel fiber reinforced concrete at 2 levels of sand to powder ratio at 1.4. Then we went up to 1.8 just, to reduce the amount of cement due to environmental reasons. And then to further reduce the amount of cement, we are using limestone as a replacement to cement at 3 further levels. And then to stay within the high range in terms of strength, we selected a water to binder ratio of 0.3. And we investigated these materials at 6 different levels of steel fiber dosages with an increment of 0.5%. And we were able to print up to a steel fiber dosage of 2.5, which is basically one of the highest reported in literature using steel fibers, which is basically a lot of steel fiber. And then based on a preliminary experimentation, we decided that the flowability range between 170 to 180 was what was compatible with our system printing system. And also we tried to control all these printing mixtures within this flowability for comparison purposes. So how did we investigate this steel fiber printable mixtures? We performed a series of tests. The first test is we looked at the printability of these mixtures, and we performed the kind of buildability test on these mixtures. And how we do this is by printing a single layer first, which theoretically should have a height of about 20 millimeter. Then we instantaneously print two successive layers on this layer at almost an interlayer gap of 0. Then we measure the deformation on the bottom layer after printing the successive layers. Then we also investigated the fresh state properties by characterizing the workability loss up to a printability window of 40 minutes. Then also we also investigated the setting time. Then we moved further to looking at the hardened state properties by investigating the flexural strength and compressive strength at 7 days. We selected 7 days due to the importance of the LEH strength of concrete mixtures for construction 3D printing. For the flexural test, we used just a single layer. We loaded just a single layer according to ASTM 1609. And for the compressive strength, we used mold cast samples. And in the future, we're also going to investigate the compressive strength of 3D printed samples as well. So now to the result. This result here shows the printability result at the sand to powder ratio of 1.4. The 3 different charts here have the 3 different levels of limestone addition to the matrix. And the major finding we've seen is as we increase the fiber dosages, we record more deformation on the bottom layer printed. So as we increase fiber dosage, we have more deformation. And also as shown in the figures right here, addition of limestone does not actually improve the buildability. So a similar trend was also seen at the higher sand to powder ratio of 1.8. However, at this high sand to powder ratio, we couldn't print at the highest fiber dosage, which is at 2.5. This was because we experienced clogging in the nozzle because of the high amount of sand in the matrix. But of course, we saw a similar trend as well. As we increase the fiber dosages, the buildability also reduces. And also addition of limestone also does not improve the buildability, as you can see in the other chart. Then taking a deeper look into why we were observing more deformation as we increase fiber dosage, we've seen that as we increase the fiber dosage, the wet density actually increased, as you can see with in the chart shown here. And so this translates to when you have increased wet density, you have more superimposed load on the bottom layer when you print. Also, we are also looking further investigating this, but we've seen that at higher fiber dosages, the rheology of this composite material might be different at lower fiber dosage. This is because, you know, to achieve the flowability of between 170 to 180, which we use for printing, we had to add more superplasticizer. So therefore, the rheology might be significantly different at high dosages. And I have 2 videos right here just to give you a demonstration on this printability. I have this video at 0% fiber. So at 0% fiber, you can see that we basically did not measure any as much deformation on the bottom layer. And then when we go up to fiber dosage of of 2.5, we could see almost about 15% deformation on the bottom layer as we print the subsequent layers. So another interesting finding we've seen is even though limestone does not improve the buildability of these layers, we've seen that addition of limestone actually improves the surface quality of these layers, and you can see this as in the figures as you go from left to right with increasing limestone addition. So to characterize the workability loss, we've seen that so this was characterized at 3 different times after the mixing procedure, and we see that workability actually reduces over time. And here we could see the effect of limestone on workability loss. That workability limestone addition actually reduces workability loss. This same trend was also seen in the sand to powder ratio of 1.8, where, but however, we saw that 10% of limestone increase the workability loss by up to 25% in the first 20 minutes. Then the conventional initial setting time was performed on these printing mixtures. And we saw that the initial setting time for the matrix was about 3.8 hours at sand to powder ratio of 1.4 and 3.2 hours at sand to powder ratio of 1.8, which is around the standard initial setting time for concrete matrices. However, we saw the effect of limestone on these printing mixtures as limestone reduces this initial setting time of this concrete matrix. And this is the classical effect of limestone on concrete matrices, which it creates some kind of luxation effect, which creates more luxation sites for the hydration process. So in terms of compressive strength, we've seen an upward increase in the 7 days compressive strength. As we increase fiber dosages, the compressive strength increase at both sand to powder ratio. Also, we've seen that the addition of limestone results in a comparable or improved compressive strength. And above a fiber dosage of 2%, there was no significant increase in the compressive strength result. Then for the flexural strength of the 3D printed samples, we've seen also an increasing trend when we increase the fiber dosage. We were able to increase the flexural strength by between 91 to 159% when we increase the fiber dosage up to 2.5. And for the IS sand to powder ratio, we're also able to have a significant increase in flexural strength at 2% fiber volume. However, we also saw that after the steel fiber dosage of 2%, there is no significant increase in the flexural strength. Mind you, this is just the 7 days flexural strength result. And also the addition of limestone powder also leads to a comparable or an increased, slightly improved flexural strength result. So just to give you an idea of these mixtures, we have 2 mixtures here, the unreinforced mixture, and when we print up to 2.5%, just to give you an idea of the load deflection curve for the single layers. And for the reinforced samples, we saw more ductility, more toughness, and more energy absorption in this. This is just for the single layer specimen, and we are working to printing standard beams, so just so we can further investigate the amount of toughness and energy absorption in this steel reinforced samples. So as next step, we are also investigating the anisotropy in these self-reinforced mixtures. And again, we were able to customize our nozzle to be able to print up to 4-inch size beams, so we can easily make standard samples according to ASTM 1609, just to investigate anisotropy in these self-printed mixtures, self-reinforced printed mixtures. So in conclusion, we've seen that the buildability of our steel fiber reinforced concrete decreases with as you increase fiber dosage. we've seen that limestone powder can be used to, improve the print quality, reduce workability, and also shorten your setting time test. And also we've seen dramatic and significant increase in flexural strength and compressive strength as a result of integrating steel fibers at high dosages. For our research, we were able to print as up to about 2.5% volume, which is actually a lot of steel fiber in the mixture. And overall, incorporating limestone powder into the cement matrix can help you achieve a comparable or higher mechanical properties for this steel fiber reinforced concrete. So with this, I'd like to end my presentation. I would also like to acknowledge the support of the Transportation Consortium South State for their support, and I'll be happy to answer any questions. Thank you.
Yeah, just curious, when you proportion your sand and cement, is it by volume or by weight?
Or by volume.
Volume?
Yeah.
Thank you.
Did you use any viscosity modifying admixtures?
For these samples, no. But in the preliminary stages, we've played with various VMAs just to see if we can improve the buildability. But for the steel fibers, for the result I've presented here, no VMA was used for this.
Have you tried using fly ash instead of limestone powder, or what's the reason?
So right now we've not tried fly ash, but we only just used limestone for now. But maybe in the future we can also, try fly ash to see the.
Yeah, because the reason is to improve flow, right? Or
So we actually incorporated the limestone just, to bring down the amount of cement we have in the mixture due to environmental reason, and just, improve the workability a little bit, which also helps with workability as well. But yeah, we can also try fly ash just to, improve the workability of these printed mixtures.